Welcome everyone to this third week live session. So, unfortunately, the previous recording was not saved in my tablet, so I'm re recording the same session. So, I'm not going to solve basically the same problems from starting, but we'll see what we did in the live session. So, I'm recording that part. Okay, so problems are already solved here, and we'll recall how we did. And so one more thing, we started with discussing as usual uh, by recalling what has been done in the classroom. So in this week we were seeing power series and radius of convergence of power series, various results related to that, and a problem solving session where we solved some interesting problems, one of them being about zeros of polynomials and its derivative. So in the complex hull was defined, and that the roots of p prime means roots of derivative of polynomial p, they lie on the complex hull of the roots of polynomial p. Okay, so this kind of some other interesting problems where classification of various isometries isometries of complex plane, that also we did, and some more questions. I don't remember all of them, but yeah. So after discussing a little bit about the content of the week, we started solving these questions. So we started with this first assignment problem where we want to know modulus of a into r, where r is radius of convergence of this power series. This power series where a is any complex number, non-zero complex number. So we want to calculate r, where r is radius of convergence. By definition, it is limit of modulus where bn, I'm writing bn z to the power n. So coefficients I'm writing bn's, and modulus of bn to the power minus 1 by n. We want to calculate limit of these numbers, these coefficients. Okay, modulus of the coefficient and their powers. So limit, we in place of bn we just write a to the power n, because a to the power n is nth coefficient in our power series. So when we write bn equal to a to the power n, so the power becomes just minus 1. So this is nothing but limit of a to the power minus 1, which is 1 by a, because for every n now this interior part is constant. So constant value is this. So limit is again the same value. So from here we got mod a into r is equal to 1, right? And that is same as modulus of a into r. So modulus of a into r is equal to 1. So this is what we want to calculate. So this way we have calculated. Here of course we see that this is used here. So the power gets multiplied when it is written like this. Okay, which is, of course, I have said that this is not same as x to the power y to the power z. If it was written like this is not equal. Okay, so after this, so I'm deleting this. This is basic calculus. I hope you know this. Right. Now in the second question, what we did, let's see. We have a power series z to the power n factorial. Then radius of convergence of power series of around the origin is. Again we want to find radius of convergence. First we write what are coefficients of this power series. Then we found that most of the coefficients are 0. So from here at least one thing is clear, that we cannot calculate by this way, an by an plus 1 modulus of this, and limit may not exist. We don't calculate this way. So this way is false, because most of the time an plus 1 is 0. So that is why what we can do here is again use the first formula for radius of convergence, which is limit of this number mod an to the power minus 1 by n. So first of all we calculate some coefficients. So most of the coefficients are 0, but it is equal to 1 when n is of this form, n is factorial of some in natural number. So 6 is factorial, 3 factorial, 24 is 4 factorial, 2 is 2 factorial. In this way the coefficients are 1, otherwise they are 0. Right, so now we want to calculate limit of these numbers. So you see, when it is 0 to the power minus 1 by n becomes infinity. That is what I am writing here. So there are infinitely many terms which are non-zero. We are going to focus on them. So because limit we want to calculate, so of course limit is not equal to infinity when it is bounded. Most of the terms are bounded, because an is equal to 1 whenever n is some n factorial, means n is some k factorial, something like that. So in that case it is constantly equal to 1. Infinitely many times it is getting equal to 1. So this becomes limit mod an to the power minus 1 by n, because this whole value becomes 1 infinitely many times. So limit becomes 1 only. So this gives us radius of convergence 1. Okay, so similarly we see in the next question, we want to calculate coefficient an is equal to 0 when n is not of this form. It is minus 1 to the power k divided by k when it is of this form, k into k plus 1 type. So in this case limit we want to calculate limit of these numbers, where, or limit of this sequence where n belonging to natural number. So an is equal to 0 part we are not going to take, because 0 to the power minus 1 by n is very big. I mean it is infinity, or we can say it is not defined in, it is positive infinity. So the biggest real number some sense, but we are going to focus only on non-zero coefficient, because that will give us if that is unbounded sequence, of course radius of convergence r will become infinity. But if we get some limit of this finite terms which are well defined, not actually 0 to the power minus 1, but remaining terms I'm talking about, which are actually real numbers. If there we get some limit of this set, then limit will be basically some real number, finite real number. Okay, not infinity. So we are going to focus on this non-zero ans. So we write them in this way. So when n is equal to k plus 1, we write here an is equal to minus 1 to the power k divided by k. So we just keep this from upside from the formula. What we get here is modulus of minus 1 to the power k is this 1. I'm not writing it in minus 1 to the power k, then modulus, it becomes 1. Okay, so now what, we solve it, the power which is in minus we make it in plus. Okay, so 1 upon modulus k becomes modulus k only. Now what, k is natural number, so modulus we are going to remove, and 1 upon k into k plus 1, that becomes 1 upon k minus 1 upon k plus 1. So distributing these powers, first term becomes k to the power 1 by k, and the second terms become k to the power minus 1 by k plus 1. Yeah, but the k n to the power 1 by n is sequence which converges to 1. So first sequence, this sequence goes to 1. What about second? Second, the power again making the power into plus, it becomes 1 by this sequence, and this sequence again converges to 1. This is the part of real analysis. If you do if you have ever solved these kind of sequences which converge to 1, so basically these two sequences are convergent and they goes to 1, so the product also goes to 1. So liminf in this particular case becomes limit. So lim-sup, if you calculate either lim-sup or liminf of these two sequences, they are coinciding and they are going to 1. So again this way we got a radius of convergence equal to 1. Okay, so in the previous question also we had radius of convergence equal to 1. Okay, so now we coming to the fourth question. Here also we want to calculate radius of convergence of a power series, where power series is given in this way. So coefficients here, an is equal to n to the power p, where p is a positive real number, so most of them are non-zero. So this division is well defined. Basically an divided by n plus 1 is non-zero real number, so here in this case it is real number, in particular, yeah, it is real number. So if it is well defined, now we want to see if limit exists or not. Once the limit exists, this limit is same as liminf of modulus an to the power minus 1 by n. So radius of convergence is also defined in this way. Okay, just limit should exist. So in the class, if you remember, lim-sup of this mod an by an plus 1 is bigger than radius of convergence, and liminf of this mod an by n plus 1 is lesser than radius of convergence. But when it exists, this limit exists, so lim-sup, liminf and radius of convergence, all these three basically coincides. And in this way we got radius of convergence equal to this limit of modulus of an divided by n plus 1. So now we put value of an, which is n to the power p, value of n plus 1, which is n plus 1 to the power p. Now after taking n to the power p common from denominator and then cancelling out from numerator, what we get is this 1 upon 1 plus 1 by n to the whole power p. Now as n tends to infinity, what happens? 1 by n, this 1 by n goes to 0, what remains? 1 by 1. So this is just 1. So radius of convergence around origin is 1. Okay, I hope you understand till now. So because it is already solved, we are not giving more times to it. If you want to focus on it, so if you have any doubt, you can leave your comments into this this video, I will try to reply, okay, because I'm not giving enough time to this, and these are already solved. Okay, so coming to next problem. One more thing, if you are not following with me, you can just stop the video and understand and then start with me, okay. So give yourself a little time to think about what is the next step, okay. Right, so now fz is given 2z plus 3 divided by z plus 1, which is a holomorphic function defined everywhere but minus 1, and it is represented by power series around 1. So disk of convergence is also given here, d1r, where we have to find value of r, so that will give us radius of convergence. And the problem 6 is about radius of convergence. Problem 5 is calculate the value of 64 into a5, right. So let's start with this. This is also after an corollary that so after a theorem where we have shown that if a power series converges on a disk, it is actually differentiable, and its derivative is given by again power series, which is also convergent on the same disk, and its derivative was basically term-wise derivation of the power series. So in that way we calculated as a corollary the coefficients of the power series can be attained by this derivative at that point divided by n factorial. So if we want to calculate an, means nth derivative at 1, because series is centered at 1, we have to calculate derivative at 1. So nth derivative at 1 divided by n factorial. This is what an is. So there are two ways to calculate an. One is actually using the formula which I am doing here right now. So if we calculate first derivative f prime z, what happens f prime z? So you solve with me. Denominator first, then derivative of numerator, which is equal to 2, and then numerator minus numerator into derivative of denominator, which is equal to 1 here in this case, divided by denominator whole square. So this turns out that numerator becomes minus 1. Okay, so you solve with me. If you want to calculate second derivative, what happens? We want to derivate the first derivative from here. So the denominator first, and then derivative of differentiation of numerator, so which is minus 1, so here we get 0, and then minus of numerator into derivative of denominator, which is 2 into z plus 1, and the denominator we get denominator whole square, so the z plus 1 whole square becomes z plus 1 whole to the power 4. Okay. Now if you see after calculation we get in the numerator 2, and the denominator z plus 1 power is reduced because of this z plus 1, so 2 by z plus 1 to the whole power 3. So you see a pattern is we are following a pattern. So minus 1 plus 2, and in the denominator powers are increasing. So let's say calculate third derivative, then we will see. So in the third derivative what happens? Right, 2 is as it is here when we write. So the first thing is we'll write denominator and then derivative of numerator, so derivative of numerator will be again 0. So I'm not writing the first part. So in the second part, what we have to write, minus and then numerator into derivative of denominator. So numerator is just 2, so minus of 2, so minus 2 is written here. Now the derivative of denominator, what it will be, it is z plus 1 to the power 3, so it will become 3 into z plus 1 to the power 2, right? Now in the denominator we get the denominator whole square, so it is z plus 1 to the power 3, so it becomes z plus 1 to the power 6. So I'm cancelling this z plus 1 whole square minus by subtracting 2 in the denominator's power, right? So we get minus 6 divided by z plus 1 to the whole power 4. So in the same manner we can calculate fifth derivative, where, so this is, see, plus 1 here and minus 1 only, sorry, minus 1 here, plus 2 here, minus 3, sorry, minus 3 factorial, which is minus 6, and the fourth will get, just because here we have 4, its derivative participated here, and it will give us plus 4 factorial in fourth derivative, and the fifth derivative we get minus of 5 factorial. This is written here. So you also calculate this, you will find this. Okay, so the fifth derivative we have calculated. Now is time to calculate coefficient a5, right? So put value z is equal to 1 divided by 5 factorial, right? So here it is. So 1 upon 5 factorial, this 5 factorial is we are taking outside. So fifth derivative at 1 is equal to minus 5 factorial divided by 2 power 6. The 2 power 6 is just we are putting well here 1, so it is 2 power 6. So 5 factorial is getting cancelled, so it becomes minus 1 divided by 2 power 6, which is equal to minus 1 divided by 64. So 64 into a5 becomes minus 1. So this is one way. There is another way, basic calculus we are going to use, expansion formulas. If you remember those things, we will see this. Okay, so coming to this second method, what we can do, this function is given by 2z plus 3 divided by z plus 1. We can, because we have to make everything in power series in z minus 1 to the power things. So we are setting these things so that z not actually z minus 1 we are taking as a variable. So in the denominator I am adding plus 1 and minus 1, so z minus 1 is here. So in the denominator we are taking 2 common, so 1 plus z minus 1 divided by 2, this appears, and the numerator part is I am taking n, because numerator is a polynomial which is analytic, and there we don't have anything that actually that is analytic, that is an entire function, that is holomorphic on whole complex plane. So the problem is on this part, which is 1 by this part, 1 by this number, and n by 2 is holomorphic everywhere, so we don't worry about that. So the radius of convergence is a radius of convergence of this. So 1 by 1 plus x has got this expression. So what I'm telling, that 1 by 1 plus x is written as 1 minus x plus x square plus and so on, right? Like this, x cube plus x4. This way we can expand 1 upon 1 plus x, and that it is actually when we talk about this is convergent in a disk, unit disk, not in the bigger set. So yeah, but here x is not uh, variable, it is actually z minus 1 divided by 2, so that we have to take care of it while calculating radius of convergence. That is the second part. But first we calculate what is fifth z minus 1 to the power 5 coefficient of this fifth power term. So we just write n by 2 as this is n by 2 into, so z to the power 4 term, z to the power 5 term we are writing. We are not writing z to the power 3 wala term just because that will not participate after this multiplication of n by 2 with this will not give us 5 power term. So 5 power terms will come from these two things only. So we want to calculate coefficient of z minus 1 to the power 5, and that will come from these two terms. So we just multiply and we'll see how many terms remains. So first z minus 1 multiplying to the first part, it will give us z minus 1 to the power 5, and the second is minus 5 by 2, sorry 5 by 2 multiplied to the fifth degree term, this, right? These two will give us 5 degree terms. Fifth power term is we are talking, and this is equal to, now we are resolving this, we are taking 2 common, so this 2 power 4 becomes 2 power 5 now, right? So now 2 minus 5 by 2 will be common in one bracket, and another bracket it is z minus 1 to the whole power 5 divided by 2 power 5. So this is minus 1 by 2, we write minus 1 by 2 in this first place, right? So from here we see that fifth degree power term has coefficient a5 equal to minus 1 divided by 2 power 6, and thus we have found that the same thing, 64 into a5 is equal to minus 1. So you can solve it in whatever way you like. Now coming to what is radius of convergence of this power series. Okay, so power series is centered at 1, so fine, we are taking center at 1, and we want to see largest disk possible where we have this power series differentiable or defined or convergent on every point inside the disk. So the problem starts at where this function is problem, that we saw that at z is equal to minus 1 there is a problem here in this point on the circle, there we have problem. So the interior part of this disk function is analytic as well as the power series expression is also analytic. So the problem is at minus 1, and minus 1 is called singularity of the function. So you will learn about singularities of a analytic function later. So right now we just see that inside this radius 2 disk, so starting from minus 1 to 1 we have this length is equal to 2. So radius of convergence is, just from the picture it is 2, and that if you want to calculate you just follow this script. Which script? So the n by 2 part is nothing, it is analytic everywhere on the complex plane. So calculate radius of convergence of this power series now, inside part, right? What is radius of convergence for this power series, which is inside the bracket, you just calculate an for this. An is given like this, right? And now you calculate this limit of an divided by n plus 1. You actually find this is 2. So this also gives us radius of convergence 2. Okay, one thing I'm using that fz has got this series expression where the first part is this is polynomial. Okay, so it is defined everywhere, it is analytic, or it is entire function. So you want to calculate radius of convergence, you just calculate radius of convergence of this power series. So that is what I did here. If you don't understand, you can write your comments. I'll try to reply. In the next session we will answer these questions which are doubtful to you. Okay, right. So now the question number 7. So fz is given by sin z divided by z when z is non-zero. When z is equal to 0, it is 1. I mean f of 0 is equal to 1. Okay, so what we did, we want to see f is continuous at 0, f is differentiable at 0, f is differentiable everywhere. So we want to see what is behavior of z. What are we doing? First we are expressing sin z in terms of power series. Okay, so you know the formula for power series expression, you just write it. Now take z common from everywhere and divide both sides. So sin z by z is a new function we are defining as gz, which is also in terms of power series. Now important thing is that in this way the power series has got almost same coefficients. Coefficients are not changing, but they are changing their places. So the limit of the modulus of an to the power minus 1 by n, if you calculate that value, so here it is written. So in first case it is infinity because sin z is an entire function, it is defined everywhere on complex plane. Okay, yeah, so is this number also. This is basic calculus from real analysis. I hope when this sequence is unbounded, this sequence is also unbounded. Some kind of comparison test you can apply. Okay, so gz is also analytic as just as sin z. It is defined on, okay, here it is written, gz has power series expression which is convergent on whole plane just like sin z. So gz is holomorphic on C, or gz is entire function, and gz is equal to, yeah, so what is g of 0? G of 0 is equal to, you put 0 on at z, so every term here becomes 0, so it becomes 1. G of 0 is equal to 1, which is also equal to f of 0. So where z is non-zero, yeah, f is equal to g on c minus 0, and at 0 also they are equal. So g is equal to f on whole complex plane, and because g is differentiable, g is continuous, this is some argument of calculating g of 0 is equal to, which is g of 0, so on zn in the c minus 0, gzn is same as fzn, and that gzn is going to 1, so 1 is equal to f of 0, so f is continuous at 0. In particularly what we can directly write, f is equal to g on whole complex plane, or don't write everything, f is equal to g on whole of c. This implies, as g is entire function, as g is entire, f is entire. That means f is holomorphic on whole complex plane. So f is of course when it is differentiable it is continuous also. So f is continuous at 0, it's true. F is differentiable at 0, of course true. F is differentiable on everywhere on C. This is what we just see, that f is equal to g and g is differentiable everywhere. So first three option fine. What about last two? So very last question is f prime is continuous on C. So that is done in the class when you have power series expression, they are differentiable, okay, in the radius of convergence, but radius of convergence is infinite in this case, so they are differentiable everywhere. So f prime is differentiable, f prime is also differentiable, f double prime is also differentiable, so they are actually infinitely differentiable, okay. F prime is continuous also, so last option is also correct. In now what about f prime at 0? You see this expression, calculate g prime which is also equal to f prime. So when you calculate g prime, here you get 0, here you get multiple of z, 2z divided by 3 factorial, and that everywhere you get multiple of z. So you put value z is equal to 0 because you want to calculate at 0. So this becomes 0, this is 2z by 3 factorial and so on. Z into something, z into alpha something, I am not writing coefficient, again z square or z cube, something like this. When you put z is equal to 0, everything becomes 0, so this is also correct, okay. So this is also correct, right. Now coming to the last question. Omega is an open connected subset of complex plane, and omega bar is defined to be those complex numbers inside omega such that their conjugate values are also belonging to omega. So to this to make our question sense, we will consider that it contains some part of real number. Omega contains some part of real number. So why? Just because omega bar, if you have, let's say, omega here, this is our omega, then omega bar is equal to empty. So without loss of generality, we will consider omega touching some part of real line, okay. In this particular way, if this is omega, this part will be omega bar, and omega bar is open subset of omega. This is from continuity of conjugation map. So this way we get an open subset of omega, which is, so there are two pictures, one on the left, another on the right. So you understand, I think. So now coming to the problem. If f is holomorphic, first problem, then so is g. G is defined to be from omega bar to c, which is equal to f of z bar. So in this case, this is wrong. Why it is wrong? We will give counter example for this. We take fz is equal to z and omega is equal to 4 of c, okay. So omega bar, in this case omega bar is also equal to whole of C. Conjugate of C is C. Now when f is identity function, what is g? G is equal to z bar, just z bar, because f of z bar will be z bar only. F is identity function, and z bar is not holomorphic. We have seen this. Okay, so A is wrong. So now about second question. Second question, if we take again same example, same thing, f identity function, omega whole of C, gz becomes fz means z, whole bar means z bar. So the just as it is good. Gz is not analytic or not holomorphic also. So okay, one more thing, analytic and holomorphic, I'm saying both things always, but this is wrong. So maybe next week you will understand why. Analytic means the function has got power series expression in a neighborhood, then we say analytic. And if it is just differentiable, we call it holomorphic or differentiable. Okay, right. So keep in mind, but in complex valued means in complex variables, complex functions from C to C functions, these two coincide. That will be later proved when we will see that every holomorphic function has got Taylor series expansion. That is, Taylor series also some power series. So we actually the both coincide in where function is differentiable in a neighborhood. Both concept coincide. So no need to worry about that right now. Just you understand that function is holomorphic, then we say it is holomorphic, right, till now. Right. So first two option is discarded, that they are not true. Now we coming to very last question. Fz from omega to C holomorphic if del f by del z bar is equal to 0. And this is also discussed in the classroom, that it is equivalent to CR equation. So when CR equation is satisfied, can you say directly that f is holomorphic? No. It is wrong. At least the theorem we have seen in the classroom is that f need to be continuous. So in the same manner, just all derivative vx, vy, ux, uy exist and they satisfy CR equation, Cauchy-Riemann equation. That doesn't mean that function is differentiable. The continuity of ux, uy, vx, vi is also important. So you just focus on them. If they are continuous, then only we can say function is also holomorphic. Okay. Right. Now we are remaining with third and fourth options. Let's see about fourth option first, then we will go to third option. What is fourth option telling us? Omega to C f is a function. J is also omega to C a function. G is defined in terms of f, fz whole bar. If f and g both are holomorphic on omega, then f is constant. Means when f and f bar both are holomorphic, then f is constant function. The proof is quite basic, I think. When f is written as u plus iv and it is holomorphic, we get this equation, Cauchy-Riemann equation, and g is written u minus iv, and because g is holomorphic, we get again from Cauchy-Riemann equation, something like this. Now if you from 1 and 2 together, you see uh, you get uy vy vx is equal to 0, ux uy is equal to 0, so everything 0. So on these lines parallel to x-axis and parallel to y-axis, function is constant, given same constant on these lines. Now one line which gives us the constant value at everything, so f is constant on whole omega. Okay, this way we have seen that f is constant and D option is correct. Now coming to C option, right? For C option we were stuck at some point, some calculations we'll do in some other way, which is of course not the way I wanted to say. In case of ux uy vx vy, these are polynomials, then we can use this formula, but in general it is not. Basically u and v may not be simple functions, so calculating ux uy everything we got messed up. So there are mistakes in these calculations, this is not correct, so that is why we are not going to use this. So we have to take care of minus sign, and so we are not going to do this way, we're deleting it. We'll solve by simple formula that, yeah, of course, that this is derivable. So note that omega bar is contained in omega, an open subset. Okay, now so we want to show G is analytic or not, right? So pick some point Z naught belonging to omega bar, because where G is defined on omega bar, and this is subset of omega, so no worries. Till now we don't have anything problem. Z naught we are going to take. So we say G is analytic or holomorphic or differentiable at Z naught if limit Z tending to Z naught G of Z minus G of Z naught divided by Z minus Z naught, this limit exists in complex plane. Or equivalently, if you take Z minus Z naught to be H, then or limit S tending to 0 G of Z naught plus H minus G of Z naught divided by H exist. So we will show that G is holomorphic at C by saying that this limit exists. Okay, claim this limit exists. How? Let's solve for it. Limit S tending to 0 G of Z naught is equal to f of Z naught plus H whole bar to the whole bar. This G of Z naught bar, sorry, YG, f of Z naught bar, the whole bar divided by H. So this limit can be written like this. Yeah, now what, this is equal to limit h tending to 0. Solving it more, we can take conjugate common, because a plus b whole bar is equal to a bar plus b bar. So you can rewrite it, f of z naught bar plus h bar minus f of z naught bar to the whole bar, using that formula, divided by uh, h also can be written as h bar whole bar is equal to h only. So you can write h bar here and everything inside this bracket, and a by b whole bar is also equal to a bar by b. So using all these formulas, we can write like this. Now what it is written inside part, so limit when h tends to 0 or h bar tends to 0, this they gives us uh, same thing. H bar tending to 0, we can replace h by h bar. And what is written inside, so one of the thing that when an converges to an bar converges to a bar. So using that formula, um, bar comes outside, limit of this inside part, f of z naught bar plus h bar minus f of z naught bar divided by h bar. So but what is inside part, do you see from here? This is nothing but f prime at z naught bar to the whole bar. Inside part is f prime at z naught, and since z belonging to z naught belonging to omega bar, z naught bar belongs to omega, and f is holomorphic, on omega, f prime at z naught bar. So it not exists, and we take bar on again, this also belongs to complex plane. So this way limit exists, and hence G is holomorphic at z naught belonging to omega bar. So z naught was taken arbitrarily, so G is holomorphic on omega. So z naught was arbitrary. So this third option is also correct. Okay, so this way we finished our session of this third week. Uh, Live session has been recorded, but there was some problem. I told you screen was stuck and only voice was getting recorded, so I had to re-record this. I have re-recorded it for my YouTube channel so that it doesn't discontinues the series. Okay, see you next week, maybe on Saturday. So fine, this is week 3 and it was dated 9th of August. Right, now we have to stop recording.